Okay, let's get started. So before I jump into the topic for today's class, I wanted to point out that I misspoke in lecture last time. And so I wanted to talk about Slater's condition one more time. And if you remember, Slater's condition is the condition that we talk about for identifying when strong duality might hold, right? So there's weak duality, there's strong duality. Strong duality means that the value of the primal is equal to the value of the dual, right? And that's a particularly nice thing for us because that means that we don't have to sit there and solve the dual to figure out whether or not it's going to be just a bound or it's exactly equal to the primal. But we have an a priori way of figuring out when this is going to be useful, right? And so Slater's condition holds for convex problems. Okay? So let's say again I have P star is equal to min f naught of x such that fi of x is less than or equal to 0. Hi of x is equal to 0. Okay? And in fact, let me not even write this as hi of x is equal to 0. Let me just write ax equal to b, because for this to be a convex problem, I want my equality constraints to be affine as it is. So I have affine equality constraints. Okay? And then we said, then, if there exists a point x naught belonging to the relative interior of the domain, which is strictly feasible. Okay, so this is Slater's condition. I talked about this last time. Everything I said about this last time was entirely correct, but I just wanted to put it up again. Here we're saying we have a convex problem. What we're trying to make sure is that, is there a point in the relative interior of the domain such that you have strict feasibility for every single inequality, okay? Now look, here we're not saying anything about whether f1, f2, f3 are affine, not affine, linear, nonlinear, whatever, right? All we know is that they have to be convex because we are saying that the problem itself is convex. Remember that Slater's condition only holds for convex problems, right? So we have this setup, and you need to have something that is strictly feasible, strictly inside the domain. Okay, you need to have this strictly feasible point, and then you can say that strong duality holds. Any questions about this before I go on to the second refined Slater's condition? The relative interiorness has nothing to do with the strict feasibilityness. These are two different things. If you're looking at a multidimensional problem, is there an easy way to tell that it's in the relative interior? You basically need to, if you can't visualize it, you will need to do it computationally, right? So you need to show that basically so what does it mean for something to be in the interior of a set? For something to be in the interior of a set in general, let's say I have some set here, let's say I have a point here. Intuitively, I know that this point is in the interior. What do I mean by that mathematically? Mathematically, for something to be in the interior, it means that I can find a ball of radius epsilon. There exists some epsilon, strictly greater than 0. It can be very small, but it exists, such that not only is this point in the interior, but everything around it is also in the interior, right? And if you notice, for a point on the boundary, such a ball is impossible to draw, right? So that is what it means to be in the interior, right? And remember, we defined relative interior last time as distinct from the interior, right? Again, I don't expect you to have to really worry about interior versus relative interior in the context of this class. For almost all purposes, for what you're worried about, looking at the interior is going to be fine. We're not intending to kind of trick you in any kind of way. But remember, as we talked about, relative interior versus interior is about this idea that, look, if an object is embedded in a space that is not kind of the true dimensionality of that object itself, right? If I think about, for example, this bean-shaped thing that I've drawn here, this bean-shaped thing I've drawn in a two-dimensional plane, right? And so I can talk about the interior of this in the context of this two-dimensional plane. But now if I was to think about this bean thing in the context of a three-dimensional space, then for a three-dimensional space, a boundary is now a surface, right? If you think about like a ball in three-dimensional space, the surface of the ball is the boundary. There's inside the ball, which is a volume. There's outside the ball. And so thinking about this bean in three-dimensional space makes the entire surface just be a boundary, right? There's no interior. And so what relative interior says is think about the object in the ambient dimensionality of the thing itself, right? Look at the affine subspace that it's embedded in, okay? So that's the difference between interior and relative interior. But again, I don't expect you to need to worry about that too much, or at all in this class. No, so the f0 of x might have a domain. So for example, I might say, I might have something saying that, I only want to consider x belonging to R plus, for example. So that means it's not f0 is just the objective function. It's just a function. The domain is something that is an implicit constraint that we don't always write explicitly here. And it's the domain, it's the intersection of the domains of all of the functions, right? So it's the intersection of the domains of f0, f1, f2, so on and so forth. Okay? We're clear on this? You guys did an example in discussion about applying Slater's condition as well, right? Yes? No? I forget if we put that on the next discussion. It's already on this discussion. X will satisfy the equality constraints, yes. So when I'm saying it's going to be in the, I see. So when I say that this is in the domain, I want the point to be feasible, right? So it's in the domain. It's in the possible set of points that I can consider. And so now let's talk about what I wanted to talk about. This is where I made the mistake last time. Relative, not relative. Okay, so here, the difference between what I call a refined Slater's condition and Slater's condition is only this. Sometimes you will have FIs that are not only convex, but are affine, right? So you might have something that is of the nature AX less than or equal to B. You might have an inequality constraint of this type, okay? And if you have an inequality constraint of this type, which is affine, then you do not need strict feasibility, okay? Just feasibility is fine. Does that make sense? So what I want to say here is now, if I have P star, I won't rewrite that problem there, but I will say that if F1, F2, all the way up to Fk are affine, then it is sufficient to have x naught such that f1 of x or f1 of x less than or equal to 0, f2 of x not less than or equal to 0, all the way up to fk of x naught less than or equal to 0, and fk plus 1 of x naught strictly less than 0, all the way up to fm of x naught strictly less than 0. Okay? So what is this saying here? If, for example, I had only affine constraints on my particular problem, okay? So for example, the linear program that we talked about last time had only affine constraints, right? There was no non-affine constraints. That's the point. That's the definition of a linear program, essentially, right? There, we don't need to worry about strict feasibility at all. We don't need to worry about whether these inequalities are satisfied strictly. Does that make sense? You can just look at whether there's a feasible point. If there's a feasible point, you're set. You cannot have an empty domain, but you have, as long as you have one feasible point, you're good. If you have a mix of conditions where some are affine and some are not affine, then you just need to check for strict feasibility of all of the non-affine constraints. Okay? I'm saying like I have m total constraints. I group them into k, the first k that are affine. I can reorder it. It doesn't matter what the constraint has what label, right? So the first k are the affine ones. K plus 1 to m are the non-affine ones. And I need to only have strict feasibility for all of the non-affine ones. Everything that's affine can be perfectly, can be just feasible, and that's totally fine. It doesn't have to be strictly feasible. And remember, when I say strictly feasible, I mean that this inequality has to be a strict inequality versus this is less than or equal to, right? This is strict less than, this is less than or equal to. Does everyone understand the difference between when I say feasible and strictly feasible? Okay, so this, I did not state this correctly in lecture last time, so go correct your notes. Do not remember the wrong thing. I'm very sorry I made a mistake on the board. But do you all have this written correctly now? Yes, you do have to worry about x naught belonging to the relative interior of the domain.
Before, the relative interior had to be strictly inside the set, right? It couldn't be on the boundary of the set?
The interior is always strictly inside. The relative interior is also always strictly inside.
And that is true, same for refined Slater's condition, like it has to be strictly inside the set as well? Because
So it has to be in the relative interior,
okay.
Which for almost all of your purposes, for this class for sure, is just going to be interior. So the question is, when do we use Slater's condition and when do we use refined Slater's condition? So Slater's condition you can always use, right? Slater's condition doesn't say anything about anything being affine or not affine, and you have the equality constraints that are affine. But you have f being f1, f2, fm being affine or not affine doesn't matter, right? So if you had affine constraints and you found a strictly feasible point, if you found something such that f1 of x naught is strictly less than 0, is it also less than or equal to 0? Strict feasibility also implies feasibility, right? So you can always use Slater's condition. You will never go wrong. Refined Slater's condition you can only apply if you have affine constraints. If all the constraints are affine, you are allowed to use refined Slater's condition, right? If every single constraint is affine, which we used in the case of the linear program last time. If you have a linear program, all you need to check for is there a feasible point? Is the domain empty or non-empty? No, we're talking about the domain of the problem. When we talk about the domain here, we're talking about the domain of the problem, which is the domain of every single function.
So all the constraints are combined into that domain.
So yeah, we talk about the intersections of all of the domains, right? So if one function is defined only on the positive numbers and the other function is defined only on numbers greater than 2, then the intersection of the domains is like all real numbers greater than 2, right? What's the difference between being in the relative interior and being strictly feasible? So the relative interior comes into play if you have, so you might have a domain constraint that is not written that is not captured by the f's. So I might have, for example, something that also says that x belongs to R plus. I might have something else like this, and then I will need to consider this point.
Wait, so isn't that a constraint?
You can think of it as a constraint, you can think of it as domain. So like there's different ways of writing these things. What is the difference between the domain and the feasible set? Okay, so that's a good question. The difference between the domain and the feasible set, you're right, we use these kind of interchangeably. The feasible set is the set of all of those points that satisfy all of the inequalities, or the equalities and satisfy all of the constraints. The domain of a function is the domain of the function. But we do sometimes use the word like the domain of the optimized. The domain of the function is basically like I have a function going from, f is going from, I don't know, like R plus to R. So for example, if I wanted to define f of x equal to square root x, then I only want to consider non-negative numbers in here, right? So that I don't get complex numbers. So then my domain is now the non-negative real numbers. I see the confusion because we do use domain and feasible set not interchangeably, but not necessarily completely separately. Here you want to think about x naught being a feasible point, and you want to think about just this interior condition. Again, I do not expect you to have to worry about the interiorness or the relative interiorness, so don't worry too much about that. Just focus on the strict feasibility part. Is the domain a superset of the feasible points? Yes. Okay, I will have to construct an example for you. I don't have one off the top of my head. But yeah, I guess one of the challenges is I'm trying to present this to you in full generality when we're not going to use it in that full generality. So don't worry too much about this relative interior business. Like, that's just not the focus of where I want to draw everyone's attention, okay? Once again, I'm sorry that I made a mistake in saying this appropriately the last time, but do you understand what I really want to make sure everyone understands is like, what do you do when it's an affine constraint and what do you do when it's not an affine constraint? Is that part clear? Okay? That's the most important thing. I want you to understand that. If you still have questions, please come talk to me in office hours. I'm happy to talk about them. And I'm sorry that the way I spoke about this last time made this confusing. Thank you very much. Okay. Good. So now let's move on to what I want to talk about today. So I want to talk first about okay. So what's a certificate? A certificate is like, when I was a kid, sometimes you go to these competitions or contests and you get a certificate of participation, right? Like it's like a piece of paper that says like, oh, Girija officially like came and stood and did this little dance for something or the other, right? Like, it's a proof of the fact that you did something. It's a proof of like proof of purchase or proof of participation or something like this. And so what dual points can be used is they can be used as a certificate of optimality. And what I mean by that is that they can be used to say that, look, here's a primal feasible point. And I can't necessarily prove to you that it's optimal, but I can give you this certificate that says it's pretty good. Okay? So let's say I have some feasible point, x1 is a primal feasible point. And let's say I have lambda 1 and mu 1, and these are dual feasible points. Okay? What do I know about the relationship between these things? Well, I know that f0 of x1 is, it's some point, and so I know that I'm trying to minimize the primal. So what is the relationship between f0 of x1 and p star? f0 is always going to be bigger than p star, right? P star is the minimum. This is some point, so this is always larger than this, right? I know this. What do I also know? I also know that p star is always lower bounded by what? The dual. But in particular, in the context, I know that, right, d star is the best lower bound. But I also know that this is true, right? And so I have this inequality as well, right? So I know that f0 of x1 is always greater than or equal to any dual feasible point, right? Basically, what the primal feasible points are always going to be larger than what the dual feasible points. Right, or there might be other constraints on the dual, right? So for example, remember last time we ended up writing duals that actually had constrained optimization problems as well, right? So sometimes we say that, look, there's multiple different options for our dual, but sometimes that our dual gets driven to be negative infinity. We obviously never want that, and so we write our dual sometimes as a constrained optimization problem as well, right? So sometimes your dual might have constraints, sometimes it might not. In general, though, you can think of it as, so when I say dual feasible, it's just whichever points are relevant for the dual. The most general case, of course, is you just have no constraints on the news and lambdas just being greater than or equal to 0. So when I think about this now, I want to think about what I want to call the duality gap, okay? And the duality gap is basically this gap between p star and d star. But now here, if I look at all of these constraints, so I know here that p star is greater than or equal to this g, right? So can I write further that minus p star is less than or equal to minus g of lambda 1 mu 1, right? This is also fair? And so therefore, can I write f0 of x1 minus p star is less than or equal to f0 of x1 minus g of lambda 1 mu 1, right? I'm just adding f0 to both sides of this inequality right here, okay? But what is this thing? This is a quantity that's very interesting to me, right? I'm trying to optimize this function f0, and now I suddenly have this quantity that's telling me how far away am I from my optimal. Do I want to be more far away or less far from my optimal? Always less far, right? So the smaller this is, the better. There's 3 quantities on this board. Which is the hardest to compute for me? P star is the hardest to compute, right? But if I give you a dual feasible point and a primal feasible point, this and this are actually less hard to compute because I'm not doing any optimization. I'm just evaluating a function, right? And so if I can find a primal feasible point and a dual feasible point, and I can look at the gap between them, that means that my primal feasible point can be no more than that much far away from the primal optimal itself, right? The gap between my primal and dual feasible points is an upper bound on the gap to optimality for that primal feasible point itself. Does everyone see that? So this means that basically by finding a dual point, I can say, well, I can't necessarily promise you that you're optimal, right? I haven't solved the dual for you. I don't even know if strong duality holds here. But I can tell you how far away you are from P star. Okay? And this usage is what is called the certificate function of duality, or like dual feasible points as a certificate. So if I can find some dual point, or feasible points, I can use this to bound how far away I am from my primal. Okay? And this is particularly useful in the context of multiple different kinds of algorithms. So for example, in gradient descent, right? We talked about gradient descent as an algorithm. And we said, well, we'll stop whenever our gradient gets to 0. But maybe our gradient isn't going to get to 0, right? In a lot of practical implementations, you don't actually get to gradient 0, especially if you have a non-convex problem. You just kind of say, well, I'm going to run for so many iterations. Or I'm going to run till my function gets below this threshold, something like this, right? There's different stopping rules that you have for algorithms. And we haven't yet talked about algorithms that use the primal and the dual, both, but we will hopefully have time at the end of class to talk about interior point methods, which will talk about how, they use both the primal, and it's an algorithmic way to use both the primal and the dual to find the optimum point. And then in those cases, basically what you can do is you can use the gap to optimality to figure out how to stop your algorithm. So you can say that as soon as I find a primal and a dual point that are only so far apart, I'm going to stop. Right? So I don't need to worry about finding P star, but by finding these 2 different points here, I can already guarantee how far away I am from optimality. Okay? So this is useful as stopping conditions for algorithms, basically. And in particular, what if I happen to find, what if? What if I happen to find such a point, or such points? What if I happen to find, I guess I should have drawn vector arrows on all of these things because all of this is for vectors. What happens if I find this magically?
Yay!
This guarantees basically I'm at the optimum, right? Not only is strong duality going to hold, but I've basically proven that this must be the primal optimal, right? Without ever actually explicitly computing the primal optimal. Okay? So this is yay, I agree. Any questions about this? Everyone with me? Wonderful question. Here, are lambda 1 and nu 1 the optimizer of the dual? So in any of this setup, we have not used that at all. We've just said that they just need to be feasible. Okay? So x1, lambda 1, nu 1. That's why I'm not using x star, lambda star, nu star. until here, no one is the optimizer of anything, right? If you find this setup, then you can therefore conclude that x1 must be the optimizer of the primal, and lambda 1, nu 1 must be the optimizers of the dual. If you find points with this zero duality gap. Does that make sense?
Then how about the second condition we wrote?
Here, this one? This one?
On the left side?
Here?
Yeah. No, the one.
This one?
Yeah.
Yeah. No, so remember, P star is always greater than or equal to every single G, right? New, lower bound, right? So you look at all of your lower bounds, you find the best one, the best lower bound is your dual optimal, but any other lower bound is also a lower bound, it's just not the best one. Yeah, so this is 0, so this is equal. So that means that's exactly what we're saying. So if Right, but this is the minimum, right? There is no relationship between x1 and lambda 1 and nu1. They're just feasible points.
Okay. They're not like corresponding.
There's no correspondence, no. If we find this, then strong duality holds, yes. In this case, if you find this. In general, up till here, we are not assuming strong duality holds. Only if you find this, then does strong duality hold, yes. By magic, yes, somehow. Agreed. So there is an element of, so why am I saying this? But you will find that often you might be able to intuitively pick out points of this nature. Second, when we get to interior point methods, you will see a systematic way for picking a lambda and a nu, like basically an iterative algorithm. So kind of how gradient descent says, like, well, x0 gives you x1, x1 gives you x2. What interior point methods will do is they will give you a systematic way of picking primal and dual feasible points, such that basically you're trying to narrow the gap between the primal and the dual feasible points. Okay, but we're not there yet. We'll talk about that very much at the end. So now I can introduce So the KKT conditions are, in some sense, a refinement or is kind of a next step of taking all of the things we've been talking about in terms of duality and condensing it down into yet another way by which we can try to find optimum values for problems, right? So duality, finding the dual, solving the dual is one way of doing it. What KKT conditions are doing are kind of giving you a way of interacting with the dual without necessarily solving for the dual or finding exactly what the dual is. Okay? So the KKT conditions kind of come in two sets. So first I'm going to talk about the KKT necessary conditions. So what's a necessary condition, right? When I say that a condition is necessary, that means that if I have a point that is optimal, it must satisfy the necessary condition for optimality, right? If optimal, then the condition must be satisfied, right? But there might be points that satisfy the condition that are not optimal, right? So this is what it means to be a necessary condition. This is different from a sufficient condition, which we're going to talk about next, right? So it's important that you kind of understand this, okay? So for this, what I want to say is that let's say I have a problem that is non-convex or convex. So convexity is not needed for this. Okay. let's say I have, yes, so that means like convexity is not necessary, right? So if it can be non-convex, it can be convex. I do not care about whether it's convex or not. Okay? I want strong duality to hold for the problem. And I want all of my relevant functions to be differentiable. Okay? I'm going to say now, I'm talking about a necessary condition, right? So I'm going to say, if you give me optimal points, then what properties must those optimal points satisfy? Okay? So if, let's say, x star is primal optimal, lambda star, mu star, so the first thing, if I have an optimal point, the first thing I can conclude is that it must be a feasible point, right? If it's optimal, it couldn't have not been feasible. So the first KKT condition says that fi of x star had better be less than or equal to 0. So all of my inequality constraints had better be satisfied, right? Obviously, if I tell you x star is optimal, it's going to be feasible. Second, is the feasibility only about inequality constraints? No. Maybe I shouldn't number these this way because these are kind of grouped together. But I can say hi of x star is equal to 0. And so what this is saying is that primal feasibility okay? Similarly, if nu star and lambda star are the dual optimals, that means they better satisfy the dual constraints. So in general, that means that lambda I star had better be greater than or equal to 0. Right? And similarly, do I have any constraints on the nu i's? Not really, right? So this is all I got. Now, the last time, we talked about this property of complementary slackness, right? And we talked about complementary slackness in the case where strong duality holds. I guess people have forgotten what we talked about last time. Okay, I'll come back to it in a minute. But, okay, aside. Remember we talked about complementary slackness? Which said, we were talking about the wine example, and we had the shadow prices for the grapes, right? We had the shadow price for Shiraz, we had the shadow price for Merlot, and if the number of Merlot grapes I had was not bottlenecking me in terms of making more money, would I spend money to buy more Merlot grapes? No, right? So the dual variable that's associated with a constraint, whether or not it's 0, has to do with whether or not that constraint is active or not, right? In particular, what you have is that lambda I fi of x, or lambda I star fi of x star, So what that means is if lambda I is not 0, then fi of x star had better be equal to 0, right? When the product of two numbers is 0, at least one of them is 0. And if fi of x star is 0, that means that the constraint is active, right? Everyone remember that? And if fi of x star is not equal to 0, that means that the constraint is inactive. And what can I therefore conclude? That lambda I must be 0. Everyone remember this? Last time we talked about this, we proved this, right? For the case of lambda star and x star being optimal points. Some memory of this? Kind of, vaguely? Okay? This means that if lambda I star is not equal to 0, this implies fi of x star is equal to 0, i.e. fi of x star is satisfied with equality i.e. it is active. It is an active constraint, right? So the optimal point is on the boundary corresponding to the constraint fi. Okay? Everyone clear on this? If fi of x star is not equal to 0, what does this imply? This implies that lambda I star had better be equal to 0, right? This means am I on the boundary now if this is not equal to 0, right? No, this means that fi of x star is strictly less than 0, right? Therefore, constraint is not satisfied with equality this is a non-active constraint. Okay? Remember, it's important to observe here that I am saying if lambda I star is not equal to 0, then I can conclude something about fi being equal to 0 or not, right? If I told you lambda I is equal to 0, can you conclude anything about fi? No, right? It could be equal to 0. It could be not equal to 0. I do not know. Okay? So you have to remember which way you can make the inferences here. What implies what? Okay? But this is why it's complementary slackness, right? Basically, if there is slack here, right? If there's a slack in your constraint satisfaction, then kind of your lambda must be 0, right? That's exactly at 0. Like basically, you have this and this, right? This constraint and this constraint. All of the lambdas correspond to these. And what this is saying is that at least one of these is going to be satisfied with inequality, with equality, right? If this is a strict inequality, then this is going to be equality. If this is a strict inequality, then this is going to be equality. Does everyone see that? That's why it's complementary slackness, right? They're complementing each other. If there's slack in one, then there cannot be slack in the other. Does everyone see that? Yes? Questions? This is a KKT condition, okay? And remember, we proved last time that if x star and lambda star are optimal, then complementary slackness must hold. Yes, question? Is it possible that both of them are 0? Absolutely, right? 0 times 0 is also equal to 0. So it is entirely possible that both of them are 0. We will see some examples of when this happens when we get to the lecture on SVMs. But in general, if you have, it's exactly possible that both are 0. That, like, you happen to have, basically what that means is that if both are 0, it means that you happen to satisfy this constraint with equality. Like the Fi happens to be equal, but it's not really relevant. It's still not the thing that's bottlenecking you. Like it's satisfied with equality by accident almost, or like it coincidentally happened to be the case, is one way of interpreting that. But it's not something you would pay to change either. Even if you change that constraint, your optimum might still not change. Okay. Good up till here? Excellent. This is not the last of the KKT conditions. So next, now, this is, I guess I should say I less than m, 1 less than I less than m. Now the last thing is that I want to connect this to the Lagrangian, right? Remember that, let's write this. Remember P star is equal to the min over x max over lambda nu of L of x lambda nu. Remember we defined, like, had this min-max characterization of how duality works, right? So now can I rewrite this somehow? What is the max over lambda nu of this, given my new notation, or given what I know now? This is the min over x of L of x, comma, lambda star, nu star. Right? Because the max of L of x lambda nu over lambda nu, I know that my optimum dual variables are lambda star, nu star. So I know that the max is going to be attained at lambda star, nu star, right? That's literally the definition of my dual optimals. Okay? So I know that this is true. And I happen to have this, that I've set condition on everything being differentiable, right? So that means that my x star must be the minimizer of this Lagrangian, right? So x star is the minimizer and therefore, if I have a problem that is differentiable, what does it mean? What is a necessary condition to be a minimizer in terms of the gradient? If you're 0, if you're the minimizer, then what must your gradient be? 0, right? So a necessary condition is that you have gradient 0 at that point. Okay? So therefore, I can write that the gradient of the Lagrangian Let me first talk through this. So what are these terms here? What is the Lagrangian? The Lagrangian is you take f naught plus you take lambda times fi, lambda I times fi, plus you take nu I times hi, right? I'm going through and taking the gradient of this with respect to x. So the gradient with respect to x here of f naught of x star, then here basically when I take the gradient of this term, the lambda i's are just constants, they fall out. I take the gradient just of this. Similarly, I take the gradient just of hi. This is all equal to 0. So remember, a lot of students confuse this. I see a lot of mistakes on exams where they write the KKT condition and they write the Lagrangian is equal to 0. Okay? Is this expression equal to the Lagrangian? No, I'm taking the gradient of the Lagrangian with respect to x. Okay? Don't make that mistake. And I'm saying that that is equal to 0. This is called the first order condition. Okay? And this is the Lagrangian evaluated at the dual optimal points. So this is not just any lambda and any nu. This is lambda I star and nu I star. Okay? So this is called the first order condition. But we're not using the convexity of anything here.
How do we know that the gradient is 0 at the minimum?
Because we remember way back when we proved something called the main theorem, where we said that if you have an optimum point, then the gradient there must be 0. We proved this well before we even started talking about convexity. We're not using convexity here. Right? So specifically holds for, sorry, this leaking sink is bothering me. We're not using convexity here anywhere. If a point is an optimum, then the gradient there must be 0, right? It's either a boundary point or an optimum, or a gradient 0 point, right? We proved this, I don't know, like in the very first or early parts of the class. Okay? Questions about this? So it's important. This is why these are necessary conditions, right? We're not assuming convexity here. We're saying if x star and lambda star and nu star are optimal, then this must hold, right? If it's optimal, then the gradient is 0, right? For convex functions, we can say it's if and only if. But here we're just talking about necessary conditions. Everyone with me? Any other questions? Okay, good. Because the Lagrangian is an unconstrained optimization problem. There are no constraints for the Lagrangian.
But lambda I can't be less than 0, right?
That's not a constraint on the Lagrangian.
Oh.
So sorry, no, it is a constraint, but that's not what we're optimizing over here. Lambda is fixed here. Unconstrained optimization. Okay, good. So now we get to KKT conditions as sufficient conditions. Okay? So now I want to talk about cases where my problem is convex and differentiable. Okay? So here I did not require any kind of convexity, right? I assumed optimality and then derived the KKT conditions. Here I'm saying I'm only talking about the cases where I have convexity from the get-go, okay? Everyone with me? Okay. So I have f1 of x, or fi of x, I equal to 0, 1, all the way up to m, are all convex. I want hi of x, I to 0, to all the way up to p, are all affine. Okay? And let's now consider x tilde, lambda tilde, and mu tilde are all points. Okay? So now, let's say I somehow get some points. X tilde, lambda tilde, nu tilde, right? Am I calling these x star, lambda star, nu star? No. These are just some points that happen to satisfy the KKT conditions. What does that mean? I basically have fi of x twiddle less than or equal to 0. Do I have to write the I equal to 1 to m every time, or like, you guys got that? You guys got that? Okay, thanks. Hi of x twiddle equal to 0. Lambda I greater than or equal to 0. All the lambda twiddles are greater than or equal to 0. I have lambda I fi of x twiddle equal to 0, so it satisfies complementary slackness. And I have the first order condition. So the gradient of x naught of x twiddle plus sigma lambda I twiddle plus sigma I equal to 1 to p nu I hi twiddle. Okay? So these are just some points that satisfy all of these conditions. Okay? Ah, yes, see? Excellent. Okay? Then I can conclude x twiddle, lambda twiddle, and nu twiddle must be primal dual optimal. By which I mean they must be the primal optimal and the dual optimal. I just was lazy to write optimal twice. Okay? So this means that if I find points that satisfy this condition, I can then conclude they must be the optimum points. Okay? These are sufficient conditions. But the sufficiency requires a different set of prerequisites, right? To say that these are sufficient conditions, I require that I'm dealing with a convex problem, right? So when I say non-convex, I mean that I'm not requiring convexity. So, i.e. convexity is not needed. So it could be convex. It could be non-convex. I don't care. Here, I require convexity. If I want to conclude that I have an optimum point by satisfying the KKT conditions, then I must have convexity. If I give you a point that satisfies all of the KKT conditions and your problem is not convex, can you necessarily conclude that these are the optimum points? No. Because here, to say that, look, what do I need to conclude? To conclude optimality, everyone pay attention here. To conclude optimality, I must have convexity and all of the KKT conditions being satisfied. If I have all of that, and means this, and this, and this, like they all have to be true, right? If all of them are true, then I can conclude optimality. But if I don't have convexity, even if I find something that satisfies all of the KKT conditions, maybe it's optimal, maybe it's not optimal, right? Because this says, if optimal, then KKT. This says, if KKT, then optimal. Those implications are two different ways, right? The KKT conditions are these conditions. This is this set of things. You notice that these conditions are the same. These are what are called the KKT conditions. They're used in different ways. Right? These equalities and inequalities are the exact same things I've written for both of these things. That is what is called the KKT conditions. Whether the KKT conditions are used as necessary conditions or as sufficient conditions depends on the context. There is no if and only if here. I have not written an if and only if here very intentionally. Right? This is a if KKT, then optimal. This is a if optimal, then KKT. So we have to prove this. We haven't proved this yet, right? So now, first take a minute and try to prove this. They're saying if these are optimal, then these are satisfied. No, it's possible that you have two, like there could be many different points that satisfy this. But some of them may be optimal, some of them may not be optimal. Entirely possible. The sufficient conditions will imply strong duality, and we'll prove that. Okay, so in the interest of time, let's do this together. So proof of sufficiency. If you're getting confused about necessary and sufficient conditions, go look up your CS70 notes. It'll be discussed there. Okay. So let's consider L of x okay? I'm considering this function of x. So I'm saying let's take the Lagrangian, evaluate it at lambda twiddle and nu twiddle specifically. Consider it as a function of x. Okay? So this is equal to L of x plus right? I'm just writing this out. So here, lambda and nu twiddle are fixed. X is a variable, okay? So I have twiddles on top of the nu and the lambda, and not on top of the x. Everyone see that? Okay. So this guy is now convex, right, by our assumption. These folks are convex by our assumption. The lambda i's satisfy KKT, therefore they're feasible, therefore they're greater than 0, or greater than or equal to 0. So now, what do we know about convex combinations of functions, right? If I take a sum of convex functions, does it stay a convex function? Still a convex function, right? So this plus this is still convex, right? I can scale a convex function by something that's non-negative. Still convex. This plus this is still convex. Okay, good. What are these hx's? Are these convex? They're affine, right? So they're convex. So is this plus this also convex? You know, news may be positive, negative, we don't care because the h's are affine, right? So this whole thing, now, is this a convex function of x, right? Wonderful. If it's a convex function of x, how do I find its minimum? Take the gradient, set it to 0, okay? So if I find a point x such that the gradient at, let's say, some point x equal to x twiddle is equal to 0, this implies x twiddle is the minimum. But do we have a point x twiddle such that that's true? Right? Our sufficient conditions gave us that x twiddle. Right? So now that means that x twiddle is necessarily the minimizer of this function. Right? Because it's a convex function and because the gradient is equal to 0 there. Okay? But what do we call the minimizer of the Lagrangian? Does it have a specific name when we take the min? Right? We have min, if I take min of over x of L of x, lambda twiddle, nu twiddle, this is equal to g of lambda twiddle, nu twiddle, right? We have a g function that's basically exactly this. Okay? This is equal to L of x twiddle, lambda twiddle, nu twiddle, which is equal to f naught of x twiddle plus hi. So x twiddle is the minimizer, but I know that, you know, the minimum of this is equal to the g function. So these things must be equal to each other, right? Is equal to this. What do I know about lambda I twiddle times fi of x twiddle? I know it satisfies the KKT conditions, right? So this thing is equal to 0. What about this thing? What is the what is true about hi of x twiddle? 0. So this thing is also 0. So this thing is exactly equal to f naught of x twiddle. Okay? So now I have some f naught of x twiddle that is exactly equal to g of lambda twiddle nu twiddle. Okay? Did we talk about something like that? I have some f naught of x1 is equal to g of lambda 1 nu 1.
Yay!
So if we have that, what does that mean? What did we say that that means? Strong duality holds, and we found the optimum point, right? By our certificate function. So this means that there is zero duality gap for x twiddle, lambda twiddle, nu twiddle, right? So by hook or crook, you've said that if you satisfy these KKT conditions, you must have zero duality gap. If you have zero duality gap, you had better be primal and dual optimal, and strong duality had better hold. Make sense? Okay? So full circle, we use the certificate function to prove the sufficiency of the KKT conditions. Sit down and read this again. You need to go through this lecture again on your own to make sure you get all the directions right. Okay? Ask me in office hours if you have questions.